All right, we've been talking about energy, work, power, how work and energy are interchangeable. Now I want to talk about how different types of energies convert from one to another and how they're conserved, one of our laws of conservation that we talk about. So it's really helpful to look at all things in kind of a mindset of energy and look at what's going on and question what type of energy is there and how is it changing. So those are the questions that I want you to start thinking about as you observe different phenomena as we go through here. The first couple slides here are kind of review or a little bit of intro about potential energy. But obviously we talked about kinetic energy, which is the energy of a moving object. That's based on the mass and velocity of the object. Velocity has a greater effect because it's squared. So if we change the velocity versus changing the mass, it has a much greater effect. So a faster moving object has a lot more energy than a slower object. If we double the speed, it has 4 times the energy. So it can do 4 times the work. So you can think of it that way as well. All right. I want to talk about gravitational potential energy. Now, potential energy is energy that's stored in something based on its position relative to a different point in time or stress or strain on the object. So gravitational potential energy is based on position. And that position is height, the relative height. So we generally set a baseline, and it depends on what we're doing, but where we set to be 0 is usually the ground or maybe the floor. So I would say that if I put something on the floor of this room, it's on the 2nd floor, it has no potential energy relative to this room, but relative to someone that's standing outside, which is a story down, it has potential energy. So it's kind of a thing that we can determine based on the situation. All right? It's dependent on the mass. Now, you might look at this formula and say, well, that's the same formula as it is for work of lifting an object, and that's exactly true. We use U for the symbol for potential energy in equations. So U sub G is the potential energy due to gravity, and it's just the weight times the height of an object. The height is measured based on what we set to be 0. All right? So the formula is exactly the same as how much work is done to lift something. So the question, how much work is done to lift something, is the same question as what is the gain in gravitational potential energy that that object has. Okay? We talked about springs a little bit. And when we talk about springs, we had these 2 equations, the Hooke's law, which tells us that how far a spring is stretched or compressed from its normal position means it changes its force of resistance. And because it changes its force of resistance, we have this formula for how much work is done, which is 1/2 kx squared. And that tells us how much work is done based on the changing resistance of something like a spring. So we can use this formula just like we do with lifting something. The potential energy in a spring is equal to the work done on the spring. So we call that elastic potential energy. Elastic means retaining its shape. It doesn't mean stretchy, it just means retaining its shape. So when something is stressed or strained beyond its normal shape, it has elastic potential energy. So anything that is not in its normal state, when it's stretched, stressed, strained, bent, and it's going to spring back, anything like that has elastic potential energy. And when that energy is released, it changes into a different type of energy. When gravitational potential energy is released, it changes into a different type of energy as well. So we convert from one type of energy to another. So the energy of a spring is the elastic potential energy. That's the work done on a spring. All right. The energy of something that has a height is the gravitational potential energy. So 2 different types of potential energies. All right. I want to talk now about conservative and non-conservative forces and conservative and non-conservative work. So when we talk about conservation or conservative forces, those are forces that whatever force you put in, you get out somehow. It's not lost in some other form of energy. All right? So the work that you do on something is stored to be released in a different way. A good example of this is gravity. If I lift something up, I don't have to do work anymore. Gravity is going to do the work back down. And however much work I put in to lift it is equal to how much energy it has at that point. And if I release it, it can do that amount of work again. That's conserved. A type of work that is not conserved is when you have a non-conservative force like friction. When I push something against a surface, that force of friction causes a different type of energy of heat, which is not a good mechanical type of energy that we can get back. It's not that the energy's gone, it's gone into the atmosphere or into the universe in a different way, and it's not conserved for mechanical purposes to retain motion and things. So this next slide, this next two slides, I have examples of this. And these are just graphical examples, and I'll show you by moving things around how that works. All right? So this is what we have with a closed path of gravitational motion. So we have this object starting at point A, and we can follow the blue line. It moves from right to left. So it's going like this. Actually, I'm going from my right to my left. So this is going from left to right. All right? And there's no work done by me because the force that I'm putting on is against gravity, so I'm doing no work. But when I lift it from B to C, I've done work. When I move it back over this way, I've done no work. But now when I let it go back down, the gravity has done the work. The work that I did to lift it over here and that gravity did to drop it down here are equal and opposite. So we see the signs mgh and negative mgh for the vertical points of the motion there. We see the work done to move it horizontally is 0 because there was no work done force times distance. My force was not in that direction or in that direction. Now, obviously, there was some friction force between my hand and the block, but we're not looking at that. We're looking at due to gravity. Okay? In friction, though, this is the same sequence of motions, but looking down on a box on the ground. And if I push that box goes from A to B, and the work that I do is equal to the force of friction times the distance. And we see the kinetic friction, mu k, times mg, so the normal force in this case, times distance. And then when I move it from B to C, if it's in a square, that's exactly the same amount of work that I have to put into it. But that work is lost. It's gone into the universe. It's gone into heating up the surfaces that are in contact with each other. It's not that it's not energy, it's just a form of energy that we can't really use to get back. It's really tough to get energy or work done out of heat. All right? So it completes that circle from B to C and then from C to D. So it has 4 times that it's moved, and every time it's lost work, the work is negative because the friction has been working against it. So that's a sequence like this. If I take this block and I move it like this, and you notice it doesn't want to have any way that it returns to where it was, like gravitational work does. It wants to return something back to where it was. All right? So we lose energy in the form of work. We do work and we don't get a return of that work. If we do work against gravity, we get a return of that work. It's a conservative force and conservative work. All right, we'll stop there. I got something for you guys to look at and do some examples of. So I'll look forward to seeing you guys tomorrow, and we'll talk more about conservation of energy. Thanks.